So, as was just announced, I'd like to talk about geometry and topology of arithmetic hyperbolic manifolds. And let me just say that in case one's going to get too excited about, I'll talk about manifolds in any great generality. Typically, I'll only talk about dimensions 2 and 3. And in the spirit of what Walter was talking about earlier, I'll also be allowing myself to talk about orbifolds because, as Walter says, it's very natural when one talks about hyperbolic manifolds that one really thinks about hyperbolic orbifolds because this allows us to think about group actions on these manifolds. Now, the topics that I'd like to talk about, at least this is my plan to talk about, is really motivated by my background in sort of low-dimensional topology, in particular three-manifold topology, and things that I would like to try to understand about arithmetic hyperbolic manifolds. And so the kind of context for the talks will be to really, again, as Walter was saying, quite often one doesn't really think just about one particular manifold. Quite often one's interested in properties of these manifolds up to commensurability, or there may be open questions regarding covering spaces of hyperbolic manifolds that I'll talk a little bit about over the course of the lecture. So really the context for this is really allowing one to talk about covering spaces or interesting finite index subgroups of hyperbolic three-manifold groups. So really the context is covering spaces, and in particular properties of finite sheeted covering spaces of these arithmetic hyperbolic manifolds and orbifolds, and the kind of features that one sees, again, using perhaps the arithmeticity to try to prove results about this. And the other context that I hope to advertise over the course of these lectures is somehow that we've heard a little bit about arithmetic groups over the last week, and again, if you haven't seen them very often, or you don't kind of wake up for breakfast thinking about arithmetic groups, then somehow it may seem a little abstract. But one thing I hope to do is to somehow give a feeling that somehow one can think of these as being highly symmetric objects. So what the other context I'd like to think about is the abundance of symmetry. And again, I'll make this precise later. And then the final kind of topic that I would like to address in these lectures, I mean, this is kind of more motivated by topology, although there'll be some geometric content later. This is very much geometric when we're looking at sort of isometries of finite sheeted covering space. And the other thing I'd like to talk about, again, is very geometric. That's the structure of the set of closed geodesics on an arithmetic hyperbolic manifold. So the structure of the set of, well, one could also say, to put in the word of lengths of closed geodesics, as well as the closed geodesics themselves. And again, what I hope to try and get over is that in the case of arithmetic hyperbolic manifolds, the set of lengths of closed geodesics is going to be very closely connected to lots of number theoretic properties of number fields and quaternion algebras that will be associated in the way that Walter described earlier. So that's really the context for the discussion. And before going on and saying a little bit about hyperbolic three manifolds and recapping a little bit of Walter's discussion earlier today, I'd like to discuss all of these in the context of the prototypical example of an arithmetic group. We've seen it earlier this week, so let's discuss this in the context. So let's discuss in the context of PSL2Z. So whatever an arithmetic group is, this would seem to be the prototypical example where we have a group that's defined by being matrices, or quotienting out by the center, where the entries are just in a particularly nice ring. Here are the integers. It doesn't get any better than the integers, perhaps. Now, unlike Walter, I won't be very careful about P and SL, because he's much more careful than I am. And I'm going to be much more sloppy about this, because it's just going to be too hard for me to keep track of P's and SL's and things. So anyway, so sometimes it'll be matrices, and sometimes it'll be PSL. So let's talk a little bit about what I really mean, perhaps, about questions that I've raised over here. So PSL2Z, as we know, lives inside PSL2R. And this is, again, as we've seen this week, it can be identified with the full group of orientation preserving isometries of the hyperbolic plane, where the hyperbolic plane here is, I'm thinking of it as the upper half space model. So this is R, and this is the positive reals. And so PSL2Z is acting discretely there. Again, Z is a discrete subring of R, so PSL2Z is a discrete subgroup of PSL2R. And as Kang, I think, showed in his talk, there is a nice polygon in the hyperbolic plane that encodes the action of this discrete group on the hyperbolic plane. So it looks something like this, vaguely. And there are identifications that are made here and here and here and here. And in making those identifications, what we see is in the quotient, we see this orbifold. I mean, this is a fixed point for an isometry that lives inside the modular group. So this is fixed by this guy. And so when we take the quotient, we see, well, this is a cusp that's developing. And again, we've talked a fair bit about cusp manifolds and orbifolds. So the picture here is this cusp that develops out. The cross-section here, because there's a two-dimensional here, we just see a little circle. So here's our little cross-section, a little circle in this case. And what we see is that there are two points on this orbifold where we have some cone angle developing from this point here, and the fact that these 2 points here identify to give us cone angle 2 pi over 3 here and pi here. So I'll just label that by a 2 and a 3. So that is the quotient orbifold. It's just a punctured sphere, or this is just, maybe to draw like this, it's just a disk with 2 cone points, one of order 2 and one of order 3. Now, when one talks about covering spaces, one really is thinking about subgroups of a group. And in the case of the modular group, there are a canonical collection of examples of subgroups of finite index that's been handed to us. And this is the kind of examples that we'll see coming up fairly frequently in the context of other discrete subgroups of PSL2R and PSL2C. So let's just talk about some interesting subgroups. So if we look at just the integers, we can reduce Z by reduction mod n that gives a homomorphism that goes to Z mod nz. And this homomorphism can be extended to give a homomorphism from SL2Z to, let's call this phi n, to SL2 Z mod nz. And so this is a finite ring, so this is a finite group. So the kernel of this guy, so the kernel So the kernel of phi n will denote as gamma n. So sometimes gamma n will be inside PSL2, but here I've written it in terms of SL2. Now, so this is a subgroup of finite index. It just looks like matrices that are congruent to the identity mod n. Now, if we take the project here we really should be careful and really think about inside PSL2 Z, inside PSL2Z. So these groups are called the principal congruent subgroups of level n. So principal. And these groups are torsion-free. So that's a slight lie because one has maybe plus or minus the identity, but when one projectivizes, we will be torsion-free. So these guys, so it's the groups gamma n, again living in, let's just say PSL2Z, are torsion-free, meaning that there are no non-trivial elements of finite order. And why is that? Well, the reason is that, well, PSL2Z is generated by these, well, plus 1 there, minus plus. So an element of order 2 and an element of order 3, abstractly, this is just the free product of the two cyclic groups, one of order 2 and one of order 3. And under these reduction homomorphisms, these two elements inject, they don't get killed. And every element of finite order in this group is conjugate to one of these two guys. So therefore, in the reduction homomorphism, all the torsion is injected, so there's nothing in the kernel, so we get something that's torsion-free. So these elements don't die under the homomorphism phi n. So we get this collection of subgroups here inside the modular group, and because they're torsion-free, they define finite sheeted covering spaces of this base, this modular surface, or the modular orbifold, which are the genuine manifolds. So there's no singular points now in these manifolds. So H2 mod gamma n is some punctured surface. So that's an interesting class of covering spaces that we get just from the fact that PSL2Z lives naturally inside PSL2R, and we get this reduction homomorphisms, and they're called, that define a very beautiful collection of finite sheeted covering spaces. Now, moreover, if you're a number theorist, perhaps you don't like gamma n so much. You prefer what's called gamma 0 n. So moreover, gamma 0 n, so this is just those A, B, C, D, and SL2Z, such that C is congruent to 0 modulo n. So for various reasons, the number theorists prefer gamma 0 n to the full congruence subgroup of level n. So somehow the theory of modular forms is much more closely tied up to the structure of this group than the group gamma n. And again, one can look at this group gamma 0 n. Now, sometimes it turns out that this actually does have elements of finite order. It's not quite as nice as this, but nonetheless, it acts on the hyperbolic plane, and we can consider this quotient. So in this case, gamma 0 n need not always be torsion-free. But nonetheless, again, we can look at H2 mod gamma 0 n, and what it looks like, it's some punctured surface again. Well, yeah. It actually turns out there's only ever two cusps for this thing, so let's just draw it like this. Now, a very classical question that somehow is in the spirit of what I'm asking over here. One wants to look at properties of covering spaces, was to understand, so this is some punctured surface with cone points, to understand what's the genus of these guys, given the n. Now it turns out that this is not a difficult question because one has tools for analyzing Fuchsian groups. The Riemann-Hurwitz formula is very efficient at analyzing what the structure of a given orbifold is, given some input data. So here we have the modular orbifold, for which we understand its area, and then we have the degree of the covering space because we know what this group is, and so we can work out exactly what this orbifold looks like in terms of the genus, the number of punctures, and the number of cone points. So a question that was an old question, so what are the n's such that gamma 0 n has genus 0. So we've already seen that somehow that the very sort of trivial case when n is 1, when we just take this guy, that's an example of the genus 0. So as I said, this can be answered using the Riemann-Hurwitz formula. And there's a short list of values of n for which you have genus 0. So given that I never remember what they are, there's not so many, but so there's only 1 less than n equal to 10, and 12, 13, 16, 18, 25. I think that, yeah, that's probably the one. So anyway, my point is less what those numbers are, rather than it's just a very short list of n's for which this very interesting orbifold has got genus 0, i.e., one way to say that is that these other guys that we see, gamma 0 n, you develop topology in this finite shaded covering space, meaning the genus is bigger than 0. So i.e., we develop topology for other n's. So we get, in the Riemann surfaces, we get some genus appearing. And in fact, there's only ever finitely many of a given genus in this kind of picture here. So the topology of these finite shaded covering spaces gets very complicated with the value of n. So that's kind of the picture that I want you to take away from this discussion here. Now I should say there are infinitely many genus 0 covers of the modular orbifold. They're not so hard to construct, but they just don't arise from this particular fashion. Okay, so that's the first part of somehow interesting subgroups. Now what about abundance of symmetries? Now what can I possibly mean by this? Well, let's just to be specific here, let's just look at gamma 0 p, where p is a prime, so I don't say anything silly. But I mean, one can do this more generally. So we just look at these particular guys here. Now, gamma 0 p is a subgroup of the modular group, so we have PSL2Z, and we have gamma 0 p, and then we've got gamma p. Now, this typically is not a normal subgroup of this guy. Why is that? Well, typically the groups that we get, so this goes down to PSL2 Z mod PZ, and of course you've known from your first group theory classes that these groups, except for small values of p, namely 2 and 3, these are finite simple groups, so there can't be any normal subgroups in this piece here. So for p not 2 and 3, PSL2 Z mod PZ is simple. So this implies that gamma 0 p is not normal in PSL2Z. So a group that encodes symmetries of a hyperbolic manifold is, what does a normalizer look like? So what we're saying here is that when you look at this little part, it's not normal, so there are no symmetries that are visible in this part of this picture. However, there are isometries that do normalize this particular group and therefore make the normalizer bigger than one might expect just by looking at this picture here. So for example, however, there exists, let's just call them tau p, in PSL2R, such that tau p gamma naught p tau p inverse equals gamma naught p. Namely, if we take tau p to be the element 0 minus 1 over root p 0. So let's just do the computation. It's matrices, so I'll probably get it wrong. So at least I'll check if I've got the thing the right way up. C times P, D, and then 0, 1 over root P. So what we see here is when we normalize, we get 0, don't tell me, minus C times root P, 0 minus D over root P, A root P, A root B, sorry, B root P, and then 0, 1 over root P, minus root P, 0. And so what we get here, keep your fingers crossed, 0 D, and then, oh good, root P cancels with a root P, so we're left with minus C there, 0, the root P's combine to give us a P here, so it's minus AP, and then 0, sorry, we get an A from that. So that is an element that lives inside the group gamma 0p. So there's this element around tau p that's not in the modular group. So this is not in PSL2Z. And yet we've found this extra symmetry that's lurking in PSL2R that we hadn't really noticed to begin with. Now, moreover, well, there's another little symmetry around. This one's orientation reversing, but let's just record it. So note also that the element, let's say, mu equal to minus 1, 0, 0, 1. So note this has determinant minus 1, so this is not an element of PSL2R. This is in PGL2R. And I won't do the dance here, but you can normalize for yourself to see that this guy normalizes the group as well. So mu gamma 0p mu inverse, sorry, gamma 0p mu inverse equals gamma 0p. So that's another involution that normalizes this group that again is somewhat bigger than one might expect. So for every one of these p's and these groups, we've constructed a new involution. And moreover, all of these involutions we've constructed from the elements tau sub p, they have to lie in different groups as well. They can't all lie inside the same discrete group. So let me just recall a basic fact about a discrete group is that if you take its normalizer in PSL2R, or if you're in PSL2C, it would be in there, is that the normalizer of discrete things are discrete. So let's just say a little fact here. That normalizers of discrete groups are discrete. So if we take this element, gamma naught p, and adjoin tau p to this, this is a discrete group, and it contains this guy as a subgroup of finite index. So this is discrete. And I claim that these tau p and tau q's, they cannot live in the same discrete group. So somehow we're really constructing lots of new groups with lots of additional symmetries that we haven't previously expected, perhaps. So note, these tau p and tau q, they can't live in the same discrete group. Now, why is that? Well, this is not hard to see either. We've got 0 minus 1 over root p 0, 0 minus 1 over root q 0. And if we take that product, what we see is minus root q over root p. We get 0 times 0. We get 0 times 0. And then we get whatever we get here. Root p over root q. So this, if these two guys lived in the same discrete group, this guy would live in that group. It's just the product of those two. Now, what have we got here? We've got groups that are, well, I've rubbed it off now, but we've got groups commensurable with a modular group. So remember, this guy here contains this parabolic. It contains this parabolic. And another fact about discrete groups is you can't have hyperbolic things sharing a common fixed point with parabolic things. So this guy cannot live inside something that's built like this. So therefore, since the group here, let's call it, delta, since delta contains parabolics fixing infinity or 0, we can't have such an element. Okay, so we've constructed a huge collection of involutions, and we've constructed, therefore, a huge class of new groups that are, what Walter was saying, commensurable with the modular group, because they contain this guy here of finite index. So this is what I mean by there's an abundance of symmetries attached to arithmetic groups, and we'll see more precise versions of this as we go along. So the last thing that I mentioned in the little discussion was that connections to the structure of the set of geodesics. So let me just say a quick word about that for now. We'll come back and say a lot more about this later. So geodesics. So here's the hyperbolic plane here, and we've got the quotient by PSL2Z, say. As we've seen, that's just, this disk with cone points. And we could look at a closed geodesic on this guy here. So here's some closed geodesic, maybe. Well, maybe it isn't, but whatever. So there's some closed geodesic on the modular orbifold. And we lift to the universal cover, and we see some collection of geodesics in the upper half plane that project down to here under the covering map. Now, if we fix any one of these guys up in the universal cover, one way to think about this is that, let's just say we look at this one here, let's call him Red, that we can find a element of the modular group. So here, there exists a gamma in PSL2Z, which is going to be hyperbolic, which means that the trace of gamma in absolute value is bigger than 2, such that, well, gamma, this is the axis for gamma, so gamma translates along here of some length, namely the length of this closed geodesic, and it closes up to give you this and projects down under this action. So, so this is the axis of gamma. So associated with this closed geodesic, we've got this element, and of course trace is an invariant of conjugation, so it doesn't really matter which one we choose up here. These are all conjugates of gamma. And notice that, well, trace of gamma, let's call that T, looks like, well, there's an eigenvalue, lambda plus 1 over lambda. So gamma here is diagonalizable, and it has 2 eigenvalues, so lambda 0, 0, 1 over lambda, and we take absolute lambda bigger than 1. So that's the trace of gamma. It looks like this. And then if we rearrange this, of course, the characteristic polynomial tells us then that, we satisfy this. And this is quadratic. Now, it's not hard to check that this quadratic is irreducible. It can't factorize here. So this turns out to be irreducible. And if you, well, solve the quadratic, what do we get? Well, we get lambda is t plus or minus the square root of t squared minus 4 over 2. So what have we just seen? To this closed geodesic on the modular orbifold, we go to the universal cover, we see this collection of geodesics, and attached to this, we see, and forget about this other part, the key thing here I want you to focus on is we get a quadratic extension. Okay, so note, so then what we want to say is then gamma is associated to a quadratic extension of Q. And again, what kind of quadratic extension is it? I mean, let me just say here, it has to be genuine quadratic extension. You know, it can't reduce, because if this reduced here, so this was a square, so that we take the square root, land up in the rationals, then this would mean an eigenvalue was a rational number. But that's going to be illegal again, because basically that is going to force the fact that you're going to have a common fixed point with a parabolic element. So if you recall, the parabolic fixed points for the action on the real numbers are just the whole of the rationals union infinity. And if you solve the fixed point equation, it's the square root of trace squared minus 4 that appears in the fixed point equation. So this guy here shows up in several places, and you can't be reducible here for that reason. So the key thing to take away is we get a quadratic extension. T is bigger than 2 in absolute value because it's hyperbolic. So this is a real quadratic extension. So this feature of associating to a closed geodesic a quadratic extension of a certain field, here, well, it's just a trace field of the group, namely we have PSL2Z, and that gives us Q as the trace field, in fact, invariant trace field in the context of Walter's discussion, means we pick up, associated to geodesics, a quadratic extension of Q. So I'm going to come back to that point later and exploit that association. Okay. Any questions before I sort of go on to talk about some more three-dimensional things again?
This calculus has nothing to do with arithmetic.
No, so this has got nothing to do with arithmetic, but one thing that can fail if you're non-arithmetic is that need not be a genuine quadratic extension. So this thing can collapse down just to give you an eigenvalue that actually does live in the rationals or with the particular field. So any hyperbolic, of course, does satisfy a quadratic characteristic polynomial over the trace field, but it can reduce to give you something that's in the trace field. And that's something that's illegal in arithmetic things, in fact. Okay. So that's really a discussion of the prototypical example and the kinds of things I want to talk a lot more about over the course of the next couple of lectures. And now I want to talk a little bit about arithmetic kleinian groups once again. So let me just let me recap or recall. You know, this is some of Walter's. So I'll recall some of Walter's talk. It won't be quite as good as his talk, obviously, but yeah, I'll recall it nonetheless. So let's talk about the description that he gave for constructing arithmetic kleinian groups. So we want to construction arithmetic kleinian groups are arithmetic hyperbolic 3 manifolds and orbifolds. So the construction was a machine. So again, as Inkang said in his talk, that there's a general machine that tells you what arithmetic subgroups are for arbitrary, say, semi-simple Lie groups. And in the particular case of dimension 3 for PSL2C, and even for PSL2R that I'll mention the slight tweak that one has to do, this construction involves quaternion algebras. So we start off from the following. So let's let K be a number field with one complex place. So there's exactly one pair of complex conjugate embeddings, but there may be a billion real embeddings. Now, again, unlike Walter, I'm typically thinking of this field as something that's embedded in C to begin with. So it's in there, you know. So So just think of that there. It's in complex numbers. So let K be a number field with one complex place. And then, so let's let B over K be a quaternion algebra. And again, one way to describe this quaternion algebra is by a Hilbert symbol. So e.g., B looks like AB over K, so where A and B are non-zero elements of the field K, and we're given B as, first of all, as a four-dimensional vector space with the bases 1ij and ij, and so we have I squared as A and j squared as B. So we've got K a number field, B a quaternion algebra over this number field, and we don't want any quaternion algebra. We want B such that B is ramified at all the real places. So again, as Walter mentioned in his talk, over the real numbers, there's two isomorphism classes of quaternion algebras, the matrices and the Hamiltonians. And the ramification means that we see the Hamiltonians. So one way to say that is, so again, so what we can think about doing is the following. So we started off with our guy B, so i.e. we have B looks like AB over K. We have a real embedding for which this place is associated to, and say sigma is a real embedding from K into R. And what we're saying about ramification is that, if we apply sigma to B here, so we get this algebra B sigma, that looks like sigma A, sigma B over the field sigma K, then when we tensor this up over the reals, this is just the Hamiltonians. And then if we look at B sigma tensored up over the reals, this is just sigma A, sigma B over the reals. And so we want that to be isomorphic to the Hamiltonian quaternions using Walter's notation. Now just notice that you may think this ramification is some airy-fairy kind of thing, but in fact it's very concrete if you're given a Hilbert symbol. Because when is it going to be ramified? It's going to be ramified precisely when sigma of A and sigma of B are both negative. Why? Well, as Professor Choi said in her talk, the Hilbert symbol is a Flaby object, but you can remove squares from the defining symbol for the Hilbert symbol without affecting the isomorphism class. So if these guys are both negatives, you can remove positive squares, and what you're left with here is just -1 over the reals. So, so ramified is precisely sigma of A, sigma B less than 0. So given the Hilbert symbol, it's a very concrete thing. Okay, so that's the setup here. We've got field, algebra, conditions at the real places, and then where do we get the group that we're interested in? Well, we'll let O be an order of B, and as Walter said, there's only one isomorphism of algebras over the complex numbers, the matrices, so we can tensor up over the complex numbers and we define a representation of B into 2x2 complex matrices. So then if we look at rho from B to B tensored up with the complex numbers, which is M2C, this defines a map of B into the complex numbers, and if we look at the elements of norm 1, so we'll let O1 equal those x and O, such that the norm, the reduced norm of x is 1, then we get rho of O1 is contained inside, and again, as Walter pointed out, on the algebra there's this involution that allows one to define the reduced norm, it's just x times x bar, and a reduced trace, it's x plus x bar, and all of these things are very natural, i.e. they respect the trace and the norm, so that the trace in the algebra here goes over to the trace over here, and the norm here goes over to the determinant over here. So this guy here lands up being in SL2C, and then if we let, say, gamma O1 to be projectivizing in PSL2 now, we get this subgroup of PSL2C, and a group is called arithmetic if it's commensurable with some group coming from a construction like this. So gamma in PSL2C is arithmetic. If gamma is commensurable with some such group, gamma O1. Now, the question was asked earlier in Walter's talk, and it's the right question somehow. Well, you know, we want things to be discrete. You know, why does this construction give you discrete groups? And let me just say a little word about that, because somehow it's kind of this argument that I'm about to sketch is that the essence of, you know, why arithmetic things are discrete. So again, depending on your perspective, I mean, somehow arithmetic things are discrete because that's what the machine does for you when you take it in the context of algebraic groups and arithmetic subgroups. But from this context, it may not be quite so clear that discreteness is coming along for the ride. And also, it's also useful to talk about the discreteness because, again, if you don't wake up thinking about arithmetic groups, and, you know, some days I don't, but you know, what has ramification got to do with this? So why is gamma O1 discrete? So let me just sketch. So what does discreteness mean? Well, indiscreteness. So if we're not discrete, there's going to be this convergent sequence to the identity. So if not discrete, there exists some gamma n that converges to the identity. So each of these gamma n's, so gamma n, say, looks like P rho of U sub n, where U sub n is an element inside the elements of norm 1. Okay, so that's what we get if we're not discrete. So in particular, you know, for n bigger than the number of atoms in the universe, or let's just be cautious and say, you know, bigger than the population of Seoul, then we get a constant such that, you know, the trace of gamma n is bounded by some constant. So in particular, there exists a constant r such that the trace of gamma n is less than some number r. Now then, we should view this as a statement at the complex place. We have these other real places that we were talking about, and at the real places we see the quaternion algebra that's Hamiltonians. So at the real places now, well, using the picture that we just have here, we get a representation of B by applying sigma and then going into the Hamiltonians over here. So we get a representation. We get, so at the real places, let me just be a little bit sloppy here, sigma, we get a representation, let's call it rho sub sigma, from B to the Hamiltonian quaternions. Okay, so that's just a composition of the things that we have over there. Now again, like I said here, the determinant and the trace, everything is natural with respect to these kinds of pictures. It has to be proved, but it's true. And so what we see here is that, well, where does, if we take something in O1 now, so let's consider the element UN inside O1. So rho sigma of UN, whatever it is, it lives inside H, but it also, because of the norm condition, it lives inside the Hamiltonians of norm 1. So if you've got a Hamiltonian of norm 1, what do the traces look like? Well, things in the Hamiltonians looks like, you know, x0 squared plus x1 squared plus x2 squared plus x3 squared is equal to 1. That's the norm 1 stuff. And so the trace, that's x0 plus x0 bar, is going to be bounded by 2. So then the trace of rho sigma UN is less than or equal to 2. Now this trace here, again, by the naturality of this, so this implies that in fact that sigma of the trace of un is less than or equal to 2. So again, this is using the fact that when we pass back and forth between kind of over here in the matrices and we pull things back, everything's the same. So what we've now seen is that, so let's call this trace Tn. So this is Tn here. So now what we have is we've got the sequence of traces T sub n such that Tn is bounded and all its Galois conjugates are bounded in absolute value. And they all have the same degree. Now it's a classical theorem in algebraic number theory that says if you look at the collection of algebraic integers, and again the traces here, Tn if you recall, because we're in an order, the traces are integers in the field k. So R sub k denotes ring of integers here. So we've got algebraic integers, all of which are bounded, and all of whose Galois conjugates are bounded, and they've all got the same degree. But there's only finitely many polynomials like that, because coefficients of polynomials are symmetric functions of the roots. And so if we bounded all the roots, we've therefore bounded the coefficients of the polynomial, and therefore the degree is fixed. There's only finitely many polynomials. So therefore, let me just sort of say by algebraic number theory, this implies only finitely many T sub n. So I won't say any more than that. That's basically finishing the proof off. There's maybe a line or two more that needs to be said, but this is the key idea that gives you discreteness. Okay, that using the ramified places gives you control of the Galois conjugates of the traces, and that's going to force discreteness. So this is a very kind of cool thing, I always thought, and it's really at the heart of many of the discreteness arguments. So let me just make a remark that, I don't think I'm going to have time to say any more on this, but it is kind of interesting in the context of the discussion that Inkang was saying yesterday, where he was looking at, representations of surface groups into various Lie groups. So what is the elements of norm 1 in the Hamiltonians? Well, it's just SU2. So in fact, what this gives you here, so note that being ramified at a place sigma implies there exists representation, let's just call it phi, from the group gamma into SU2. And one can put this in the general framework that Walter talked about, the invariant quaternion algebra, so that if you're unramified at a real embedding, you get an SL2R representation. So being unramified at sigma implies that there exists phi that goes from gamma into SL2R, and these are faithful representations of the group into SU2 and SL2R. Okay. So that was the construction of arithmetic kleinian groups. Now, amongst the arithmetic ones, the non-compact arithmetic hyperbolic manifolds are somehow the easiest to describe. So let's make a remark on the non-compact arithmetic orbitals. So non-compact means that we have these cusps now, and we have these parabolic elements inside the group. Now, as Walter discussed in his talk today, when you have parabolic elements, that corresponds to having zero divisors inside the algebra. So in the case when we're non-compact, you have to be a matrix algebra. And then the ramification condition says, well, what can the field K be in that case? Well, it can only be quadratic, because if you had any real embedding for the field, well, you would have to be just M2K, that's because of parabolics. But we've already decided in the definition, we're ramified at all real embeddings, so you can't be M2R if you have to be the Hamiltonians. So the non-compact arithmetic orbifolds, the construction starts with k is q root d, q root minus d, so d here is positive and square free. And the algebra, we take b to be m2 q root minus d. And let me just write in a word. Why? Well, so from Walter's lecture today, so non-compact implies there exist parabolic elements. Parabolic elements implies there exist zero divisors. Zero divisors mean that I throw the chalk away. So zero divisors mean that we must be the matrix algebra. So we must be isomorphic to M2K. Okay, but why do we get quadratic imaginary? Well, the reason is that if we tensor this up over the reals, we just see the matrices. So this looks, as Walter said, locally this is M2R at the real embeddings. So this is locally M2R at real embeddings. However, that's illegal because the condition in the definition of a construction of the arithmetic groups is that we're ramified, and so we have to be Hamiltonian. Okay, but implies we're ramified at a real embedding, a real place. So that's a contradiction. So the only thing we can have must be this field. It's a field with one complex place. And so there we go. Okay, so the non-compact arithmetic hyperbolic orbifolds is defined by matrix algebras over quadratic imaginary number fields. So, and within that, the commensurability classes can be organized. So the basic examples was mentioned in Sue Young's talk the other day, the Bianchi orbifolds, or the Bianchi groups. So these are the groups PSL2 OD, where OD is the ring of integers. And q root minus d. So every non-compact arithmetic hyperbolic 3 orbifold is commensurable with your quotient of H3 by these guys. Now, Sue Young drew some of the orbifolds associated to these. So let me just draw some of these just because I want to make some points about this. So if we look at H3 modulo PSL2 OD, so this looks like, so these are somewhat more organic than Sue Young one. So in the case of D equals 1, so what you should think of here is that this is the 3-ball, that's the base of the orbifold, and then there's some singular locus, that's this little graph here, and the labelings that indicate the cone angle is 2, 2, 2, 2, and a 2, and a 3, and a 2, and a 3. So, meaning that we have an elliptic element of order 3 that corresponds to this part of the singular locus. So we have the 3-ball, and schematically this orbifold looks like there's one cusp, and we take a cross-section of the cusp, you have to see a Euclidean orbifold there, and what it is, it's a sphere with 4 marked points of order 2. So those are the pillowcases that we talked about the other day. So this is D equals 1. And let me do D equals 3. It's a similar kind of example. So we'll see 3, 3, 3, 3, 2, 2. So that's the case of d equals 3. Again, the underlying space for this orbifold is the 3 ball. And if we look now at a cusp cross-section, we see this sphere with 3 mark points this time, a 3, a 3, and a 3, meaning we see a Euclidean triangle orbifold in that case. And now let me just do one more, just to illustrate some difference I'd like to remark on. So for d equals 2, it's different. So this is d equals 2. So this is the open solitaris is the underlying space, and then so here's this. And here we've got this very simple singular locus in this case. So we have the solitaris with 2 strands, one labeled 2, one labeled 3, and a little arc that joins them. And you may wonder, well, why is there such a difference here? Here we had the 3 ball in both of these cases, and here we had the solitaris. Well, now what's going on here? And the reason is that this is explained by number theory. The fact is that in the rings of integers, so the key little fact is that these rings don't have many units anyway, but when d is different from 1 and 3, the only units in OD are just plus or minus 1. And when d is equal to 1 or 3, well, we can see plus or minus I as well, and plus or minus omega bar, where omega squared plus omega plus 1. 0 is some cube root of unity. So what's the relevance of this? Well, the relevance is that this shows up here. You know, why do we see this ball appearing in the quotient? Well, the fact is that in the particular Bianchi group, we see the element I, 0, 0, minus I. So this fixes infinity, notice. So therefore, if one looks at the peripheral subgroup of the Bianchi group when d is equal to 1, fixing infinity, there is this element of order 2 as well as translations. Here, you only ever see translations. And in this case here, you see an element omega 0, 0, omega bar. So this has order 2, and this has order 3. So you get some extra symmetries in the cusps of these orbifolds that you don't have here because you have non-trivial units in these rings. Okay, so that's why these orbifold pictures are different from all other Ds. They can be much more complicated than this, but that's kind of the key reason. Now, again, as Walter mentioned in his talk, one passes to finite sheeted covering spaces, which are manifolds. One can always do that. There are torsion-free subgroups of finite index. And again, as Walter was advertising, arithmetic things seem to somehow occur just remarkably often in nature, given the fact that they should be very rare, given the statement that, you know, below a given volume, there's only finitely many arithmetic things. So some of the very nice covering spaces that one sees for these cusp arithmetic manifolds have a particularly nice place in the development of hyperbolic 3 manifolds. So let me just so there are some interesting finite sheeted covers. So again, from the point of view of the start of the lecture when I was talking about finite sheeted covering spaces, is that for me? So there are interesting finite sheeted covering spaces. So for example, you know, what could interesting mean? Well, as in Craig's talk today, he was talking about knots and links in the 3-sphere. And some of the ones that have a particularly important place in the development of the subject are this one, where if we take the complement of W, then S3 minus W covers the orbifold. So let's call these orbifolds Q sub D. Covers the orbifold Q sub 1, so the complement of this nice link is the Whitehead link. And then for d equals 3, let me skip 2 for a minute. So for d equals 3, we saw this earlier. Let's see if I can draw it. I was practicing. So there's the figure 8 knot, and we saw that this guy here covers Q3. And in the case of d equals 2, there's a nice one. I'll need my picture for this. I can't do this freehand. Better people than I can do this, but not me. Well, I thought I drew it. Maybe I didn't draw it.